Next, there is the proof by cases. So take an example. Assume that we have for all x and y real numbers. The absolute value of x times y is the absolute value of x times the absolute value of y. The idea of a proof by cases is simple. Basically, you split the proof into a finite number of cases that cover all the possibilities. Such a proof will often happen if you are confronted with absolute values, because you can then make a distinction between positive numbers and negative numbers and the absolute value of those. So you just split, you look at all the different options that there are, and you prove them one by one. In our case, we have two numbers, x and y, so we will get four cases. X can be positive or negative, and y can also be positive or negative. So we will split this proof in four cases. The first case, x and y are both positive. The second case will be x is positive but y is negative. The third case would then be that x is negative but y is positive. And then the final case, case number 4, is that both of them are negative. And then we prove case by case. So if x is positive and y is positive, this means that the multiplication of x and y is also positive. So it means that the absolute value of x times y is just x times y itself because it is positive. So this is then x times y, but since x is positive, this is the absolute value of x times the absolute value of y. Case 2, x times y is negative, so then the absolute value of x times y is minus x times y. This is x times minus y. X is positive, so x is equal to its absolute value, and minus y is also equal to the absolute value of y because y is negative. And then we continue the same way. Here, third case, the multiplication is also negative, but we now split it differently. So xy is minus xy. This is minus x times y, which is equal to the absolute value of x times absolute value of y. And then the fourth case, the multiplication is positive. So the absolute value of x times y is x times y. This is also minus x times minus y, or the absolute value of x times the absolute value of y. And so we've shown for all four cases that this multiplication is true, that the absolute value of x times y is equal to the absolute value of x times the absolute value of y. And then the last method that we will cover here will be a proof through mathematical induction. So this is a very important part. Mathematical induction is a proof technique which can be used if you have a number of cases which follow logically, so which are associated with integer numbers. For the example, let's take a look at the sum of the odd numbers. So we have the first odd number is 1. 1, the sum of 1 with 1 is 1. This is equal to 1 squared. If we look at the first two odd numbers, so 1 plus 3, this has a sum of 4, which corresponds to 2 squared. The first one, so 1 plus 3 plus 5 is equal to 9, corresponds to 3 to the power 2. 1 plus 3 plus 5 plus 7 is equal to 16, so this is 4 squared. 1 plus 3 plus 5 plus 7 plus 9 is 25, which is equal to 5 squared. When we look at this row of examples, the conjecture that we can make is that the sum of the first n odd numbers is equal to n squared. So this is our conjecture, this is what we assume that might be true and what we have to prove. So we will call this statement P. We will then also add numbers to indicate which statement we are referring to. So for example, P1. P1 is the first statement. So it's the first statement saying that the sum of the first odd number is equal to 1 squared. Similar, P2 will say that the sum of the first two odd numbers is equal to 2 squared. P3, you get the sum of the first three odd numbers, which will be equal to 3 squared, and so on. So you see here that we have an indication with natural numbers. So the first statement, the second statement, the third statement. So mathematical induction only works if you can make a statement for the natural numbers or for a part of the natural numbers. So we have to have such a sequence, such a follow-up that is increasing one by one. Mathematical induction always consists of 3 steps. So the first step is your basis or your start point. Here you prove that your first statement, so P1, is true. Then the second step is the induction hypothesis. So this is a hypothesis for the induction step. You assume that the statement is true for some case. So you assume that Pk is true. So for any number k, this is an assumption that you make. And then the third step, this is your induction step. So here you will use that Pk is true to prove that also Pk plus 1 is true. So again, you start with the basis, you start with showing that the first statement is true. So you prove that this first statement is true, it is your starting step. Then you assume that Pk is true for any number k. So you just make this assumption. So you assume this is true and you will use this in your third step, in your induction step, to show that Pk plus 1 is also true. Why is this sufficient to finish the proof? Because basically this way you have proven the statement for every possible number. First you prove P1, so you prove the starting point. If P1 is true and you have shown the induction step, number 3, this also means that P2 is true. If P2 is true, again the induction step tells me that P3 is true, and so on and so on. So if I show that my first one is true, and then I can show that if Pk is true, then also Pk plus 1 is true, I have basically shown that my statement is true for any natural number. If we then move back to the example that we want to prove, we can write this down mathematically. So the general formula would be Pn. Pn is the sum of my first n odd numbers. So this is 1 plus 3 plus 5 and so on, plus 2n minus 1. And this should be equal to n squared according to my conjecture. If we then do the proof, step 1, we have to show P1 is true. So you just plug in the value 1. So the left hand side, so the sum of my odd numbers is 1. The right hand side, this is 1 squared. So these two, they are the same. So my first step is true, is trivially true. The second, we assume that pk is true. So basically we assume that 1 plus 3 plus 5 up to 2 times k minus 1, that this is equal to k squared. And then the third step, if I know that pk is true, I have to prove also that pk plus 1 is true. So we have to prove that 1 plus 3 plus 5 and so on up to 2k plus 1 minus 1 is equal to k plus 1 squared. So we have to prove the next step in my sequence of statements. First observation that we can make, this is 2k plus 2 minus 1, so this is 2k plus 1. And then we will show that the left hand side is equal to the right hand side. We start from the left, so the left hand side is the sum. It's 1 plus 3 plus 5 plus 2k minus 1 plus 2k plus 1. We then use the induction hypothesis. So we use the second step, and we know from the second step that this is equal to k squared. So in your third part, in the proof for pk plus 1, you will always have to use the induction hypothesis. You always have to use the second step. If you don't use the second step there, then something is wrong with your proof. So we have, this is k squared plus 2k plus 1, which is just k plus 1 squared, which is equal to my right hand side. So I have shown all the steps of the mathematical induction. So we have proven that the general statement is true, that the sum of the first n odd numbers is equal to n squared.